Good morning. Thank you all for being here. Really appreciate it. So I'm excited to talk to you guys about the use cases that we're thinking about at DOE. And let's see here. I'm going to give a little background on my office at the Department of Energy and also talk a little bit about the various collaborations and the ways that we're thinking about use cases, how we're exploring them. We're working very closely with the Quantum Economic Development Consortium. They've been a great partner in the process for us. We've worked on some reports and workshops, so I'll go through some of them, and then also talk a little bit about some of the other areas that we're thinking about. There are applications that benefit the energy sector, even though if we would be deploying them in the space setting. So just really quickly, the Office of Technology Transitions has only been around for about 5 or so years, maybe 6 now. We serve as the front door to the Department of Energy. So we are essentially herding cats. We are looking at ways to commercialize technologies all across the various program offices. So many of you are probably familiar with the Quantum Information Science Centers. They were funded primarily through the Office of Science. That's one half of DOE. There's a whole other half that focuses on renewables and energy efficiency and optimization and security. Those are the applied programs. And so our office is trying to be a bridge, not just between the Department of Energy and the private sector, but we're also trying to be a bridge across these various offices and be able to move technology development from fundamental research into the applied programs and ultimately into commercialization. Now, at the same time, our office helps to move these technologies along and create partnerships and demonstration projects. But at the same time, we're also doing some market development like work, because we believe that if you build it, that doesn't mean they will come, right? You actually have to work the land so that the seeds of technology have somewhere to flourish and to grow. So we are trying to think about technology development in a very holistic way. And as you could imagine, given that half of the Department of Energy is focused on the energy sector, hence the name, not just fundamental research and science, then it makes sense that we would want the energy sector to also be a customer of quantum technologies. And so that is another way that's another thing that we're thinking about, and I'll talk a little bit more about some of those ideas shortly. So obviously, if you're looking to commercialize a technology, you have to think about the use cases. So we've got a lot of smart engineers and physicists that are thinking about how to get these things to work, to have fidelity, to be viable, to answer questions. But then there's a whole other exercise that we have to go through, which is, well, what are we going to use it for? What questions can we ask? What are the use cases? And so we're spending a lot of time digging into that. And that is the work that we're doing internally across the various offices in the applied programs, but also with our external partners and working with industry very closely. So we're looking at doing workshops, bringing people together that haven't actually spoken together, don't talk necessarily the same language, and trying to get them to understand each other so that we can actually think about how can we use these technologies in a way that will benefit industry and also keep interest within the development of quantum technologies, right? Because we are all concerned about a quantum winter, and we don't want that to happen. So we need little nuggets of success along the way to show that there is something that we can take away along as we develop the process and develop these fault-tolerant quantum computers. But there's all this other stuff that we can use in the meantime that we want to explore. So one of the first steps we decided was, let's take a look at optimization. There's a lot of interest in quantum computing, but we're thinking about, well, are there some near-term applications? Are there things that we can do today with quantum annealers or with NISQ computers? Because some of the questions that we can look at in the grid space, they don't have to be precise. They don't have to be exact. It's all about probabilities, and so we're comfortable sometimes making decisions based on these probabilities. So we decided to bring together folks from academia, from industry, from the labs, to talk about just grid optimization. Let's just focus on that near-term where we have computers that, like quantum annealers that can actually maybe answer some optimization problems. That seems to be potentially the low-hanging fruit on the computing side. So we brought all these folks together, put them into different teams, made sure that there was a representative that understood quantum computing, understood algorithm development, applied mathematics, energy industry problems, and put them all in breakout sessions together and had them facilitated. And Accenture was a phenomenal partner in helping to facilitate these discussions for us. And then we talked about how do we take the grid and make it into a smart grid. Everyone's talking about grid modernization and grid 2.0. What exactly is that? Well, when you think about where the grid is evolving and where we're going today, it's becoming a two-way flow network. We have data, immense amount of data that has to go both ways, and electrons are going both ways. We're actually making the grid more dynamic. And so it's becoming a very complex system. And the math geeks out there, the first thing they'll think about is, well, this could be a great optimization problem, right? Like how do you optimize all these various assets that are interconnecting with the grid that the utility may not necessarily own, but needs to have visibility? It's becoming a very complex network. And we also have now renewables connecting, electric vehicles connecting, and electric vehicles aren't just pulling energy from the grid, they're also putting energy back on the grid. They're bi-directional. And just to give you a little perspective, Nissan Leafs today are all bi-directional. They've been that way for more than 10 years. And a lot of that has to do with Fukushima in Japan and the Japanese wanting, your vehicle to be like a backup generator for homes during emergencies. Those Nissan Leafs today, if you add up the battery capacity that they provide just in the US, already exceed the amount of battery capacity that stationary storage offers the grid today. That's an immense amount of capacity that, if we could harness it properly, could provide a lot of value. And then if you are following EIA's estimates, they estimate that 130 million vehicles will be electric by 2030. That could represent 10 times the amount of energy storage that the grid needs today. It's an immense amount of power and capacity, and then you don't have to use more rare earth elements to build stationary storage that could do the same thing. Obviously, there are different use cases where stationary storage makes sense and where mobile storage could make sense, but as you can see, like, these are things that the grid has to grapple with. How do you provide power to all these new assets that are going to be connecting to the grid, and then how do you harness those assets? It's a very complex problem, and it's all going to be happening at the edge. It's going to be happening at the distribution level. So building transmission lines is not going to help. The pain points are going to be where everybody is, in the cities and in the distribution network. So this is a great optimization problem. So these are the types of things that we talked about in this workshop. And we built a matrix to think about, well, what are the different applications that we could use for quantum computing? We can use we obviously have applications for machine learning, for optimization, for simulation, and we thought about it in the different segments that we like to break the grid into. We think about it in terms of, the customer, the aggregator. As you could imagine, if you're going to have all of these distributed electric vehicles, someone's going to want to aggregate them and figure out how to optimize that. And we already have aggregators today for solar and other types of renewables. We have the distribution network, as I mentioned, which is where a lot of this activity will take place. And you've got the transmission and the generation side. All these things have to be optimized, and they flow together, and they all interconnect. It's an immense amount of interdependency between these various areas within the grid, and it has to flow and work together. So after we did this workshop, we synthesized up the takeaways and developed a report. It was just published, I believe, last week. Yes, just last week. So it took a while to get it out there. Had to go through a significant approval process, but there were some key takeaways where, some great optimization problems that we could look into that the industry was interested in is fault tolerance and fault prediction, energy market optimization, and then integrated planning and optimization for reliability and the resilient grid. And as you can imagine, that's a lot of these different assets. They're going to fall into these buckets that are going to be interconnecting with the grid. You want to optimize the assets that you have that are participating in the market. You want to plan for when you're going to want to use different types of assets. And then obviously quantum chemistry and simulation for new materials was of great interest. Another area here that we're exploring is quantum charging and quantum batteries. There's been some preliminary research that was done in the US and then was taken further by the South Koreans, that on paper shows that you could build these quantum chargers and quantum batteries that could take a supercharge down from, if you go to a DC fast charger today, it takes about 30 minutes to fully charge. You could reduce that to 3 seconds. And home charging could be reduced from 3 or 4 hours to 30 seconds. So this is an exciting area for us to think about for charging, because it would make it easier than going to a gas station. It's faster than going to a gas station, and you never have to leave your home, which is even more exciting. So there's a lot of exciting areas for us to look at in terms of quantum applications in the energy space. So obviously optimization is not the only thing we're looking at. There are other problems that you are all familiar with, but the optimization piece is on a computing side is the easiest for us to dig into. And this is a nice way of sort of looking at the different types of problems that quantum computing can answer. And all of these different types of math problems apply within the energy space as well. So the other thing I wanted to talk about is quantum sensing. And I also chair the Quantum Sensing Technical Advisory Committee within QEDC, so I'm a huge fan of sensing. I think it is the low-hanging fruit. It's one of those technologies in the quantum space that I think could just provide credibility overall to the industry. And there's a lot of applications, and it's been around for a long time. It's been proven. But there's also opportunity for us to apply some of these quantum sensing technologies in new and novel ways. And so at DOE, we're interested in timing and inertial sensing and magnetic field sensing and electric field sensing, because we can apply them in many different ways. So I mentioned, these electric vehicles are going to become assets to the grid. Well, we're going to care where they are. The position, navigation, timing becomes very critical, especially if the grid is going to have to send out market signals to say, hey, we need power here, and this electric vehicle is not that far away. This is an information flow and an exercise where there's going to be a democratized, decentralized type of activity with the grid. And so timing is going to matter. And we don't want to depend on GPS all the time. GPS is easily spoofed and jammed, and there are parts of the grid that are GPS denied. So timing is of interest, and even inertial sensing. And then magnetic field and electric field sensing also have all these different applications. But on the energy side, we're interested in using these quantum sensing technologies for anomaly detection on the grid, right? And we can also use it for exploring, oil and gas and geothermal, finding caverns underground that could be used to store carbon, for example. So we have interest in all the different flavors of quantum sensors, and we also have some lab folks working on some new and novel materials in quantum sensing. So this just goes through a little bit more on the different types of atomic clocks that we've explored within the QEDC, and that we're also looking at it at DOE. And as I mentioned, there's strong interest in these portable, low swap optical atomic clocks. We're going to probably want them in our vehicles, want them on the grid and in different assets. This one talks a little bit about the inertial sensors, and the navigation is of great interest to us, but obviously DoD and other folks as well. So we are working very closely with some of our sister agencies on some of these technologies, because we're developing them, but we're looking towards the industry, see what they've done, and there's an NV defect gyros is another exciting area, because it's supporting very small platform applications. So this just goes over the list of the different electric and magnetic field sensors, and we don't have NV diamond on here, but that's another exciting area that we're really looking into, and it's sort of emerging. So this gives us a little snapshot of, you know, the maturity and the different types of sensors as they lie on the landscape. This one focuses more on national security, and as you can see here, you know, there's plenty of options here for commercial viability today. And then this slide captures the private sector opportunities. So this again was developed internally within the Quantum Economic Development Consortium's Technical Advisory Committee on Quantum Sensing. And this is a living document and graph, let's just say. So we're looking for input. These are going to be moving pieces. This was our best guess at the time, but we know that there's been a lot of development, and so this will obviously need to be updated over time. So I want to talk a little bit about the space opportunities here. So as I mentioned to you, you know, we care about knowing where things are that are moving through space, right? So a lot of networking, a lot of the work that's been done today, particularly with DOE, has been based on networking within using fiber. But as I've described to you, the energy sector obviously is not going to be beholden to just applications that are connected to fiber. We have things moving through free space, so we care about what is moving through free space and how that's going to interact with the grid. And so space-based applications do actually have applications for those moving assets. And so we're interested in secure communications. How do we secure it? How do we liberate ourselves from GPS, which is not always going to be reliable and can be jammed and spoofed? And what are the different types of images that we can capture right from space that could help us with monitoring the grid, monitoring wildfires, looking at climate change, and doing climate forecasting so that we could optimize our grid. So there are many different types of applications that would be useful in a space setting, and this would include quantum computing. I know people are like, put computers in space? Yeah, you know, DoD is looking at putting data centers in space. And so these are things that we're looking at and looking to partner on because we have mutual interests in being able to process information that's captured in a space setting and then be able to retrieve that information and send it down. So as I kind of touched on already, we are interested in using these space-based applications for carbon storage, for navigation, position and timing, for detecting resources underground. We obviously care about timing for the grid, and we don't want to always be relying on GPS. And then remote imaging has applications that are of great interest to the department. This was just a quick snapshot. There's a typo at the bottom, explore benchmarking. We are looking at benchmarking, but it wasn't supposed to be there. But you know, there are FOAs that are going out that address climate change or that address optimization in the grid. They may have the words quantum, they may not, but that doesn't mean that quantum can't be part of the solution. It just has to fit in the overall mission that DOE is supporting. And then I just wanted to highlight a couple of things that we've done already. Obviously, fusion has some great potential, and we think that quantum sensing and quantum computing could help us along that path. And we've done some exciting things in the labs, and we've done some entanglement work that is taking, you know, quantum networking to another level. And then quantum chemistries is obviously very exciting as well. So I know I need to wrap up. So with that, I want to leave you guys with Feynman's famous quote. You may have heard him say that because nature isn't classical, and if you want to make simulation of nature, you better make it quantum mechanical, but it's going to be hard. He also said that we need imagination, and that imagination is a terrible straitjacket. So we are trying to think outside the box. Sometimes that might mean that we sound a little crazy, But that's where innovation comes from, and that's where disruptive innovation comes from. And if we want to achieve these moonshot ideas, then we're going to have to go there. Otherwise, we'll have to answer to the sky. Thank you so much.
We do have a few minutes for questions. So questions for Rima, please.
Hi, great talk. So my background is like in condensed matter physics, computational chemistry. So most of my interactions with DOE have been trying to use your resources for, running simulations. And I know that there have to be decisions made when you're scaling up new HPC clusters, like is AMD going to provide the GPU? Who's going to make the CPUs? And as you start to think about incorporating like QPUs in those, has your office, thinking about like commercialization, started to vet, hey, we think ion traps are going to be the one? Or so, I mean, maybe you can't answer that, but I'm curious.
No, I'm glad you brought that up, because I will admit, we have 5 QIS centers. All of them are working on superconducting qubits.
Okay.
And obviously we know that there's more than that, right? There's neutral atoms and trapped ions and others, and some of them are working on more than that, but that is something that we noticed and said, hey, is that a great idea? Should we expand? And so we have like Oak Ridge National Lab that is partnering with private sector companies that are developing these other technologies and providing access to them. And I think we want to grow and expand that further. There is interest in developing user facilities, not just for fundamental research, but for the applied program. So this is something we're thinking about. And obviously, if we're going to support user facilities for applied programs, we're not going to want to be beholden to just one type of computer, because we don't want to put all our eggs in one basket. So we are thinking about that. And I think through this applied effort, we'll be able to broaden our capabilities.
Okay, thank you.
Any more questions for Rima? Oh, I'm sorry.
I'm curious if you guys are coordinating with the Air Force, because they have a big program. Is there overlap? Is there collaboration? How does that work out?
There is collaboration, and there will be I don't want to get ahead of myself, but you'll probably be hearing some things soon. But we are talking on a regular basis, and I've had DoD on the slide before. I took it out. I'll put it back. I just didn't want to get ahead. But yes, we are talking to DoD, and I think you'll see some things exciting coming out in terms of the collaborations there, because we have mutual interest, and I think there's opportunities for us to leverage each other's resources, where we're going to be using scarce government resources in a much more efficient way if we're working together. And we see those opportunities, and we are working through them.